Ever wondered how your favorite music app instantly sorts thousands of songs, or how GPS finds the quickest route to your friend's house? That's all thanks to Algorithms, the step-by-step recipes that power every smart decision in computing. In this course, you'll learn how to design these recipes, analyze how fast they run, think BigO, and apply them to real-world puzzles like scheduling tasks, searching data, and optimizing routes. By the end, you'll be able to craft your own efficient solutions and predict their performance before you even write a line of code. Let's dive in. Now that we've introduced the course, let's cover the logistics. This course is taught in English, and all materials, slides, notes, and recorded lectures are available online for distance learning. Chinese and English videos are posted on eCourse2, so just visit ecourse2.ccu.edu.tw to access them. We follow a 16-week schedule, and if you ever miss a live session, you can catch up anytime on our YouTube channel, where all past lectures are archived. You'll only need to come to campus for the midterm and final exams. Finally, all homework assignments and online quizzes are submitted through the course platform. Now that we've covered the course logistics, here's how your performance will be evaluated. You'll complete 2 homework assignments, each worth 15% of your final grade, and 2 online quizzes, 10% apiece. In Week 8, you'll sit for a midterm exam that counts for 25%. And in Week 16, your final exam carries another 25%. On top of that, you can earn up to 10% extra credit by actively participating in our online Q&A sessions. Your TA will determine if your contributions are meaningful. Finally, all homework and exams will be graded using AI tools. Now, let's dive into how a typical homework or exam on Fibonacci recursion is processed through AI grading. On the left, you'll see the original assignment. Implement the nth Fibonacci number by recursion, analyze its time complexity, and suggest optimizations, paired with a sample handwritten solution that uses memoization and tail recursion. On the right, the AI grading interface shows a near-perfect 98 out of 100, with the score broken down into 3 criteria: problem comprehension, solution approach, and code efficiency. Under each heading, the system provides targeted feedback. Just below that, you'll find a polished, system-generated summary of the student's answer. Finally, 2 important reminders appear. You're welcome to share jailbreak attempts on eCourse2 for bonus discussion, but any unauthorized submission will automatically reset your score to 0. Now that we've seen AI tackle a recursive Fibonacci assignment, let's turn our attention to the primary textbook for this course. Introduction to Algorithms by Corman, Leserson, Rivest, and Stein, now in its 3rd edition. This comprehensive reference covers fundamental algorithmic techniques, everything from sorting and searching to graph algorithms and dynamic programming, and pairs rigorous analysis with practical implementation advice. We'll lean on it all semester long for clear explanations, step-by-step pseudocode, and hands-on exercises that reinforce each topic. Building on that solid algorithms foundation, let's dive into 2 key texts on approximation methods. First up is Vijay V. Vazirani's Approximation Algorithms, Springer 2001, which offers a systematic introduction to designing and analyzing approximation techniques. Then, we have Dorrit S. Hochbaum's edited volume, Approximation Algorithms for Nitrogen Monophosphide Hard Problems, 1996, a classic compilation of fundamental results and practical algorithms for tackling tough optimization challenges. Together, these books give us both the theoretical underpinnings and a wealth of real-world applications in this exciting field. To complement these foundational texts, here's our primary online resource, a dedicated YouTube channel packed with graduate-level algorithms lectures. Just click the link on the slide to subscribe. In the screenshot, you see a grid of hour-plus videos, each titled CCU Graduate Algorithms, and posted between October and December 2020. Topics span PTAS and LP relaxation flows to classic nitrogen monophosphide hard problems like MaxCut, set cover, bin packing, and knapsack, as well as sorting and SAT. Whether you need a quick refresher or want to dive deeper, these recorded sessions let you learn at your own pace. Now that you've seen our graduate-level lecture series, let's dive into problems and algorithms. In grad school, you'll tackle challenges from diverse fields, and even when you're building large systems, there are always core issues demanding rigorous theoretical analysis. At its essence, an algorithm is simply an ordered set of rules designed to solve a specific problem. Traditionally, we pair those rules with formal mathematical proofs, scrutinizing time complexity, space requirements, and correctness. But in everyday conversation, algorithm has broadened to describe almost any idea or approach. Building on that foundation, today we're asking a big question. With generative AI tools like GPT-4 and Claude 3.5 Sonnet becoming ever more powerful, do we still need to master every classical algorithm ourselves? Think about sorting routines, graph traversals, string comparisons, or dynamic programming. These building blocks of efficient computing aren't going anywhere. Sure, large language models can spit out code on demand, but a deep understanding of these algorithms lets us judge correctness, squeeze out better performance, and handle those pesky corner cases. In this talk, we'll explore how human expertise and AI support can complement each other to shape the future of algorithm design and problem solving. Building on our earlier discussion, let's look at how GPT-4o really performs with algorithms. First off, it can correctly solve roughly half of our homework and quiz questions, complete with formal proofs for certain algorithms, clear walkthroughs of time complexity analyses, and fully working implementations. But it's not perfect. When problems get more complex, GPT-4o can still stumble. You'll see incorrect answers or flawed proof slip through. Even though about 95% of its code compiles and runs, subtle bugs often remain hidden. Bottom line? You still need to understand every line of generated code to debug, validate, and trust the solution. Building on our earlier discussion of AI-driven algorithms, let's dive into the two pillars of practical performance: hardware and software. On the hardware side, we can squeeze out efficiency with MPI for message passing, OpenMP for multi-threading, SIMD vectorization, careful cache miss tuning, GPU acceleration using CUDA, and even elastic scaling in the cloud. On the software front, picking the right data structures and crafting efficient algorithms delivers dramatic speedups. By combining these hardware and software optimizations, we unlock peak performance in real-world applications. Building on those hardware improvements, let's dive into OpenMP, a simple yet powerful way to add shared memory parallelism to your C or C++ code. OpenMP is just a set of compiler directives, but it makes parallel programming surprisingly easy. In our first example, we declare an array of 256 doubles and then insert dot #pragma omp parallel for dot right before a standard for loop. This directive tells the compiler to split the loop iterations across multiple threads, with each thread computing table equals 2*n in parallel. Next, we switch to coup #pragma omp parallel sections dot to define two independent code blocks. The first section runs a loop that prints hello 100 times, while the second prints world 50 times. Both sections execute concurrently on separate threads, showing how effortlessly you can parallelize distinct tasks. These snippets demonstrate that with just a few OpenMP pragmas, you can turn sequential loops and code blocks into parallel workloads, significantly boosting performance on multi-core systems. Now that we've seen how OpenMP parallelizes loops across threads, let's zoom in on data-level parallelism with SIMD, single instruction, multiple data for vector programming. On the left, you see four separate additions: A plus B, A plus B, A plus B, and A plus B, each producing C through C in four distinct operations. The C code below reflects that. You declare the arrays and write four individual statements to compute C0 through C3. On the right, we use SIMD. The same arrays are aligned on 16-byte boundaries and cast into vector pointers. Instead of four separate instructions, a single vec_add call takes the entire vector of four integers from A and B, adds them element-wise, and stores the result in C with one operation. That means 1 plus 2, 3 plus 4, 5 plus 6, and 7 plus 8 all happen in parallel. The key takeaway is that SIMD packs multiple data elements into one register and processes them with a single instruction. dramatically boosting throughput for data parallel workloads. Building on that SIMD speedup, here's a real-world example of hierarchical parallelism in action. At the top level, 3 processing units exchange data using MPI. Inside each unit, OpenMP launches 3 threads to share the workload. Finally, each thread exploits a 4-lane SIMD engine for fine-grained data-level parallelism. By combining MPI across nodes, OpenMP across cores, and SIMD within threads, we unlock maximum scalability and peak performance. Now that we've seen how MPI, OpenMP, and SIMD work together for maximum scalability, let's turn our attention to another key performance factor: data layout. Here, we're comparing 2 fundamental structures: arrays and linked lists. An array packs all its elements into one continuous block of memory, so you can jump straight to element 3 or element 7 with a simple index calculation. A linked list, by contrast, stores each value in its own node, and each node points to the next with an arrow. To move from one element to the next, you follow those pointers one step at a time. When we perform a sequential sweep through every element, arrays usually win. Because their data sits side by side in memory, they take full advantage of the cache, delivering faster and more predictable access. Linked lists, on the other hand, incur an extra cost every time you chase a pointer, so their traversal ends up noticeably slower in practice. Building on that comparison, let's dive into what happens when a cache miss forces the processor out to main memory, dramatically slowing down execution. At the top, you see the key takeaway. RAM is orders of magnitude slower than on-chip cache. Sequential array access usually hits in cache and blazes through data, whereas random access patterns in lists, trees, or graphs often miss and incur a costly trip to RAM. Below, the diagram illustrates a typical multi-core CPU. Each core has its own private L1 and L2 caches, while all cores on the chip share a larger L3 cache. If data isn't found in L1 or L2, the core checks L3 before finally reaching main memory. Cache misses at any level introduce significant delays, underscoring why data locality and sequential access are so critical for peak performance. Building on our earlier look at cache hierarchies and memory access costs, this slide shows how real-world performance gains come from both hardware and software improvements. On the hardware side, we leverage MPI for distributed process parallelism and OpenMP for multi-threading. Apply SIMD vector instructions to crunch multiple data elements at once, tweak memory behavior to reduce costly cache misses, and tap into specialized resources, from GPU acceleration with CUDA to elastic, on-demand cloud instances. On the software side, choosing the right data structures and crafting efficient algorithms form the foundation for maximum throughput and responsiveness. Together, these hardware and software strategies drive efficiency and push practical applications to peak performance. Now that we've explored hardware and software-level optimizations to boost performance, let's shift our focus to algorithmic efficiency by looking at common time complexities in Big O notation. First up, a hash function delivers constant time, O1, since it computes its result in a single step. Next, binary search, having the search range with each comparison, runs in logarithmic time, O log n. Finding the ith largest element in an array can be done in linear time, On. Merge sort, with its divide and conquer approach, achieves On log n. By contrast, insertion sort, with its nested loops, slows down to quadratic time, On squared. And at the far end of the spectrum, a straightforward recursive Fibonacci implementation grows exponentially, on the order of roughly O1.5 to the power of n. Understanding these distinctions lets us pick the right algorithm for the problem size we're tackling. Building on our overview of Big O complexities, here we compare 6 common growth rates as the input size n increases from 1 to 20. You'll notice the logarithmic curve stays almost flat, showing very little growth. The linear line rises steadily, with the n log n curve just above it. Next, the quadratic curve climbs more sharply, and the cubic curve grows even faster. Finally, the exponential curve starts low, but then soars past 1,000 by n equals 10. This visualization makes it clear that algorithms with quadratic, cubic, or especially exponential time quickly become impractical as n grows. which is why we always strive for the lowest possible complexity in real-world applications. Building on that explosive exponential curve we just saw, let's dive into a classic example, the naive recursive Fibonacci algorithm. We define fib_n as 0 when n equals 0, 1 when n equals 1, and otherwise fib_n1 plus fib_n2. On the slide, you'll see this mathematical definition alongside a simple C implementation that checks if n is 0 or 1, then returns fib_n1 plus fib_n2. Because each call spawns 2 more calls, the total number of calls, and therefore the running time, doubles at each level. Pretty soon, even moderately large n becomes completely impractical. To solve this efficiently, we need to avoid all those redundant computations by using techniques like memoization or bottom-up dynamic programming. Building on our look at exponential blowups in naive recursion, let's now turn to another pair of graph traversal puzzles, Euler-Tours versus Hamiltonian cycles. On the left, you see a subdivided square with a continuous red path that covers every edge exactly once. That's an Euler-Tour, and finding it is actually straightforward. Just verify the graph is connected, and every vertex has even degree, then trace the tour in linear time. In the center, we have a more intricate 5-fold pentagon of pentagons in plane outline. And on the right, we highlight one possible Hamiltonian cycle, visiting each vertex exactly once. But unlike the Euler-Tour, no polynomial time algorithm is known for Hamiltonian cycles. They're nitrogen monophosphide complete. So even though these problems sound similar, one is efficiently solvable, while the other is believed intractable. Building on that Hamiltonian cycle idea, imagine you're a traveling salesman faced with a network of cities, each connected by roads with specific travel costs. Your goal is simple: start at one city, visit each of the others exactly once, and then return home while minimizing your total cost. On the left, you see a tiny 4-city example. Cities A, B, C, and D are fully linked. 20 units between A and B, 42 between A and C, 35 between A and D, 30 between B and C, 34 between B and D, and just 12 between C and D. Even with only 4 stops, finding the cheapest loop isn't trivial. On the right, we zoom out to a real-world challenge, a map of Germany showing an itinerary through Berlin, Hamburg, Cologne, and Munich. This is the classic traveling salesman problem in action, optimizing routes across multiple locations to minimize total travel cost. Building on our exploration of route optimization, today we turn to another classic challenge, the K-coloring problem. In this problem, you're given a graph and asked to assign one of K colors to each vertex so that no 2 vertices joined by an edge share the same color. On the left, you see a small 5-vertex graph successfully colored with 3 colors, red, green, and blue, demonstrating a valid 3 coloring. On the right, a partially completed Sudoku grid serves as a special case of graph coloring. Each cell is a vertex, and edges link cells in the same row, column, or block, ensuring no 2 adjacent cells carry the same number from 1 to 9. Our key question is, does deciding whether a graph admits a K-coloring belong to the complexity class NP? Building on our discussion of NP problems, let's turn to one of the most fundamental, the satisfiability problem, or SAT. SAT asks, given a Boolean formula, can we assign true or false to its variables so that the entire formula evaluates to true? In complexity terms, SAT sits squarely in NP. If someone hands you a candidate assignment, you can plug it in and check each clause in polynomial time to confirm it really satisfies the formula. Let's see this in action with a concrete example. Consider the conjunction of these 5 clauses over variables x, y, and z, da not x or y or z, da not x or y, x or not z, z or not y, not x or not y or z. All you do is substitute the proposed values for x, y, and z into each clause. If every clause comes out true, you verified that the formula is indeed satisfiable. Now that we've seen how SAT exemplifies NP verification, let's zoom out and preview our journey ahead. First, we'll tackle asymptotic analysis and divide and conquer techniques, powerful tools for designing and assessing efficient algorithms. Next, we'll survey key polynomial time problems, from dynamic programming to string indexing and classic graph algorithms. Then, we dive into the core complexity classes, PNP and nitrogen monophosphide completeness. Learning how to prove a problem is nitrogen monophosphide complete by reduction. After that, we'll explore approximation algorithms, covering deterministic methods, randomized approaches, and relaxation techniques. We'll then confront inapproximability results to understand when good approximations simply aren't possible. Finally, we'll wrap up with polynomial time approximation schemes, rounding out our exploration of algorithmic performance and limitations. Now that we've mapped out the entire syllabus, here's how to reinforce your learning. Be sure to visit the eCourse2 portal regularly and work through the lecture videos at your own pace. You can access all course materials at ecourse2.ccu.edu.tw. And we've also uploaded additional recorded lectures to our dedicated YouTube channel. Bookmark both links and carve out time each week to review the videos. This little habit will keep you right on track